Unit 3 Chemistry, Chapter 7, Part 1. This area of study we're looking at the rate and the extent of chemical reactions and how that can influence how much energy is produced from them. So, we remember our energy profile diagrams, of course, and we remember that the reactants, let's go to the products, the activation energy is always positive because that is the energy required to break the bonds. And if the energy released when we make bonds in the products is less, we have an endothermic reaction. If it is more, then we have an exothermic reaction in which heat is given out to the surroundings. That's true, but sometimes that happens slowly and sometimes that happens fast. And we can change how fast it happens by changing the rate of a reaction. So the rate is going to depend on the temperature, the concentration of the reactants, the pressure of gaseous reactants, because if we increase the pressure we're essentially pushing the particles closer together, the surface area if it's a solid, and whether or not we've got a catalyst. All of them affect one of two things, or sometimes both. They either affect how frequently a collision occurs, or the frequency of collisions that have got sufficient energy to break the bonds in those reactants, which we call activation energy. Okay? It is important to realise that a chemical reaction is only going to happen if two reactants collide with enough energy to overcome activation energy. It can be more than that, but if it's any less, then they're just going to bounce off each other without changing. So, start with the surface area of solids. If we've got a solid, then it's only the particles on the outside that are able to react. Any that are in the middle can't react. So if we break it up, keep the same number of particles but break it up, we're increasing the number of particles that are on the surface, and therefore increasing the number of particles that can be involved in the reaction. So the frequency of collisions between the solid and other reactants increases. And if that increases, we get a faster rate. The other thing we can do is increase temperature. Now this works whether we've got solids, liquids, aqueous solutions, gases. If we increase the temperature, we increase the kinetic energy. So if we increase the kinetic energy, what that means is they're moving faster. So they're going to bang into each other more often. Also, if we increase how fast they're moving, we're increasing their energy, so more of them are going to have activation energy. So temperature increases both the frequency of collisions and the proportion of collisions that are successful. Okay? So that's why it has such a big effect, because it does both. All of the other factors we're going to look at only do one or the other. Okay? We can look at that with these curves, which are called Maxwell-Boltzmann distribution curves. And I only mention that because that term is mentioned on your study design. Okay? You don't need to remember the names of it. So this is the average kinetic energy of substances at a set temperature. Let's say it's 20 degrees. And what you'll see is some of them have got very high energy, some of them have got very low energy, but most of them are somewhere in the middle. If we increase the temperature by 10 degrees, what we're going to do is increase the average kinetic energy. We're still going to have some that are very high and some that are very low, but the average is shifted to the right. Okay? Now if we then draw on our activation energy, we will see that at that point here, if we look underneath the 20 degree line, only those particles there are going to react. If we look underneath the 30 degree, well, we've increased the area under the curve there. Okay? And by increasing the area under that bit of the curve, then we've got more particles there, so more of them are going to react. Concentration and pressure work in the same way as each other. Okay? Basically, more stuff in the same volume. Okay? So, we're going to increase the frequency of collisions. We're not going to change the proportion that are successful, we're just adding a greater number of them. Okay? So, it will increase the rate of reaction. So if 1% of them were successful, and at a low pressure or a low concentration, we had 10 collisions per second, well, then you're going to get 0.1 of a collision. But if we increase the concentration to 100, well, then we're going to get 1 reaction per second. Okay? Still working at 1%, but the number of collisions goes up. Catalysts. These apply to any type of reaction, but catalysts are specific. Okay, so we have to find the right catalyst for the right chemical reaction. There's two different sorts of catalysts. Both of them lower the activation energy, but they do it in different ways. Homogeneous catalysts, homo means the same, so they're in the same state as the reactants. And those make a new pathway. And those new pathway, even though we have the same start and the same end molecule, okay, we have a lower activation energy at all of those steps, so that increases our rate of reaction. Because a greater proportion of the molecules will have activation energy if the activation energy is lower. Okay? When you make your final product, you regenerate your catalyst, so your catalyst, whilst it's involved in the reaction, doesn't get used up. The other type is your heterogeneous catalyst, hetero meaning different, so a different state to the reactants. Okay? These would normally be a solid, and the reactions can adsorb to the catalyst, normally by dispersion bonding. That might cause some bending and stretching in it, which lowers the activation energy, okay? And then we make new bonds in our products, and the products desorb from the catalyst and go back off into the solution or as gases.